In this section, we are going to take a look at linear approximations. So the whole idea behind a linear approximation is if you took a curve, and it could be any curve. In my example here, I have a blue curve drawn. This could be maybe an exponential graph, or maybe it's part of a polynomial. It doesn't matter. But the idea is if you pick a point and you zoom in enough times on that curve there, eventually that curve looks linear. Therefore, the tangent line, which is what I have drawn in red on my graph here, the tangent line essentially becomes a really good estimate for the actual curve if we're really close to that point. So we call that a linear approximation when we're using a tangent line to approximate a curve. So my curve here that I have in blue is the curve f of x. My tangent line we have labeled as L of x. So if you look at the graph to the right, you can see that for values of x very close to x equals a, and if you want to go ahead and mark that on your graph, here's our value of x equals a, then we're saying that the function in blue, which is f of x, it can be approximated using our tangent line, which I have labeled as L of x. And this is the concept known as a linear approximation. Sometimes people call this local linearity. So the linear approximation is just a tangent line approximation. So there's really nothing new when we do linear approximations because we've been working with tangent lines for a long time. We're just going to be writing equations for tangent lines. So the linear approximation of f of x at x equals a is going to be given by the following equation. L of x is equal to f prime of a times the quantity x minus a plus f of a. Now this looks like a pretty complicated formula initially, but I want to show you where this comes from, because you'll realize this is really just the equation for a line written in point-slope form, essentially. So let's work on where this comes from. So again, we have our curve, and our curve is what I have graphed in blue. Sorry about that, which could be our curve f of x. And then we have this point, and so the x value of my point is a, therefore the y value of my point is f of a. So the point that we have on the curve is a comma f of a. And then if we want to write the equation for the red tangent line, then we need the slope of the tangent line. And in calculus, we know the slope of a tangent line is the derivative. So the slope of the tangent line in this case would be f prime of a. So if we write the equation for the tangent line, and we have both a point and a slope, then we can use the point-slope form of a line, which would be y minus the y value of our point, which is f of a, is equal to the slope, f prime of a, times x minus the x value of my point, which is a. So now we'll go ahead and just solve for y by adding f of a to both sides. And that'll give us y is equal to f prime of a times the quantity x minus a plus f of a. And notice this equation that we just wrote here is exactly the equation that we wrote above. The only difference is, instead of calling this equation y equals, they replace y and they replace it with L of x. So they write L of x is equal to f prime of a times the quantity x minus a plus f of a. So this is just an equation for the tangent line, with it labeled as L of x instead of y. And we call this line the linear approximation of f of x as long as x is close to a. Because as you can see, if I were to move farther away, let's say I'm over here, if I move farther away and I look at the tangent line's y value compared with the actual function's y value, you'll see here that there's a tremendous difference between these y values. But if I'm sitting close to A and I go to the tangent line and compare the tangent line's y value with the actual y value on the curve, those y values are very, very close to each other. So that's why we're always saying that the tangent line is a good approximation as long as we are close to A. As we get farther away on either side, the tangent line isn't going to be as good of an approximation at that point. So let's work through one example. Determine the linearization, which is another name for a linear approximation, of f of x is equal to natural log of x at a equals 1. So whether your textbook or professor calls it a linearization or a linear approximation, either one of these terms means we're just writing a tangent line equation. That's it. This is a tangent line equation. And to write the equation for any line, we know we need two things. We need a point and we need a slope. So let's start with our point. It's telling us that we want a to equal 1, so that is the x value of our point. Therefore, we need to find the y value, so we will substitute 1 into our function. And remember, our function is f of x is equal to natural log of x. So if we substitute 1 in, then we're computing the natural log of 1, which is going to be equal to 0. Therefore, our coordinate will be 1, 0. That's our point. Next, we need our slope. Now, our slope will be found by computing the derivative. So we need to find the derivative of natural log of x. The derivative of natural log of x is going to be 1 over x. So now let's find the slope at x equals 1. So f prime of 1 divided by 1 is equal to 1. So this is going to be our slope. So now using our point and our slope, we can use the point-slope form of a line and just write the equation for the tangent line. So y minus the y value, which is 0, is equal to our slope of 1 times x minus the x value of the point, which is 1. So this is essentially y is equal to x minus 1, which is a perfectly acceptable answer. However, when you typically look this up in a textbook, they will again label this, instead of y equals, they'll label it as L of x is equal to. So L of x is equal to x minus 1. Either answer is acceptable, they're equivalent, they're both the equation for the tangent line at the point where x is equal to 1.